This is the fourth episode of my more intuitive model of quantum mechanics. In this episode, I want to talk about entanglement and macroscopic quantum phenomena. So, as in all my videos, I'm using these two postulates. First one is that quantum objects are instantly reformable wave packets, all part of one thing, and that they might instantly reform when they're interacting, depending on how much of them is interacting, according to the Born rule, where a probability of collapse to region is proportional to the squared amplitude. In the first episode, I go over these two postulates in depth. If you haven't watched that, you might want to. Anyways, in the previous episodes, I've talked about varying the size of the wave packet versus its wavelength, and that gives us the uncertainty principle. And then I talked about confining wave packets, and that gives us electrons around the atom. In this episode, I want to talk about allowing wave packets to interact and sort of join into one thing. And this is going to be dealing with entanglement and macroscopic quantum phenomena. The first thing to talk about in this presentation is superposition. Superposition is where you have a bunch of waves and they add up to create a new wave state. So here you have two waves passing through each other, and as they do, you get an increased amplitude. With quantum superposition, the particle or instantly reformable wave packet is in a mix of various possible states. So you have a bunch of different properties that the wave packet can have, such as spin, energy, momentum, polarization, and position, and it's in a mix of a bunch of possible states. So there's a range of values that it can take on for momentum or energy or polarization or what have you. And it's in a superposition of a bunch of different values. So it'll settle upon one of these values when you measure it. So here you have a wave packet, and it's in a superposition of a few different momentum states. And it's a superposition of a bunch of different position states. So the position distribution is quite broad, whereas the momentum distribution is kind of sharp. And the way this wave packet is constructed is adding an infinite number of waves. A lot of them are basically around the same frequency, and thus you have this sharp distribution for momentum. So it's a superposition of momentum states and a superposition of position states. And if you go to measure it, it'll settle upon one of those position states. So you measure position, and you no longer have a superposition of position states, you just have one spot. Whereas now you have a broad superposition of momentum states, and the way this wave packet is constructed is through a bunch of different waves that are of different frequencies. And another example of superposition is spin. So you have this wave packet coming in to get detected, and before it's detected, it's in a superposition of both spin up and spin down. And then once it's detected, and say in this case spin down, it settles upon one of those values and it's no longer in a superposition. So in this conceptual model, how do you understand entanglement? Well, if you leave two wave packets close to each other, or you create them from another packet, they can become entangled. Now in this conceptual model, it seems best to think about it as the two packets are inhabiting or occupying each other. So here you have wave packet A and wave packet B. A is red and B is blue. And A has a presence in B and B has a presence in A. So I've drawn them as alternating crests, red and blue, and that's to suggest that they're occupying each other. It doesn't suggest that A's crest is alternating with B's crest in each one, not at all. They're just trying to get across the point that they are entangled and thus inhabiting each other in a sense. So you let them get detected, and when B is detected, B's presence instantly leaves A, and A's presence instantly leaves B. And that upon detection, they stop occupying each other, they stop being entangled. So if you want to consider this in terms of spin, if you have A in a superposition of spin up and spin down, you'd write it like this. And with B is spin up and spin down in superposition as well, you write it like that. Now what if you have them both spin up and spin down, but they're also entangled? Well, the way you write that mathematically looks something like this, where you have A spin down and B spin up as one sort of basis for your state, and then A spin up and B spin down as another sort of basis. So you can't write this mathematically with them separated, you have to write them together. And the way I'm sort of putting that is that they're inhabiting each other. So here's A and B and spin up and spin down superposition. If they're entangled, A is inhabiting B as spin up and spin down, and B is spin up and spin down inhabiting A. And then when you let them go off and get detected, suppose B is spin down, A immediately becomes the opposite, spin up. Now, in this conceptual model, I think this all makes a great deal of sense, but I don't think you could reason out that A would be the opposite spin of B, but I think this makes a great deal of sense from what I've been saying. So in one sense, they're becoming part of one thing in a limited way. So not only can you have spin up and spin down, you could also have spin out of the page and spin into the page. Now, if A and B are entangled as spin up and spin down, they are not entangled as spin out of the page and spin into the page. Those are not entangled states. So it's a limited sort of one big wave packet thing when they're entangled, but in another sense, they are part of one big wave packet, part of one thing. Now, as I've been saying, measuring one instantly affects the other because they're instantly reformable wave packets. And you might think you can use this to send messages faster than light, but you can't. That violates special relativity. And the last thing to say here is that entanglement can be delicate. Not always, but can be quite delicate, because if you have two things entangled and a stray photon comes in and collapses the state, then the entanglement is ruined. So in the laboratory, you want to keep things probably very cold or something like that to guard against this. So quantum computing is a direct application of entanglement. So with quantum computing, you have a qubit instead of a bit. And these are simply instantly reformable wave packets or particles, and they're in a superposition of states. And then you entangle them with many other particles. So a simple example would be this linear ion trap computer, where you have a bunch of atoms that are ions that are sitting next to each other for a while and trapped in place. And because they're sitting next to each other, they become entangled. Now, if you go and measure the state of one of them, that instantly reforms all of them. And if you have a whole lot of these, you can treat that as part of your computation. And you can get a whole lot of computation done with just one shot. And then you reset them, entangle them again, and then measure them again, and you get more of your computation done all at once. So instead of having to compute every last thing, you can compute a whole bunch of things at once and get the probable answer to your problem. Now, we're starting to build these quantum computers, and apparently they're starting to get as fast as the best computers of today. So in the future, we should have very, very powerful quantum computers that work like this. So quantum coherence is something that's related to what I've been talking about with entanglement and having one big wave packet. So when waves are coherent, they have a constant phase difference. So here's two waves that are completely in phase, and that means when one is peaking, the other one is peaking, one is troughing, the other one's troughing. Here's a 90-degree phase difference. So one of them is at 0, the other one's peaking or troughing. And then we have 180 degrees phase difference, and one's peaking, the other one's troughing. And the thing about all of these examples is that they're all coherent because the phase difference between the waves is always the same, no matter how far you go. Now here's two waves that aren't coherent because they have different wavelengths. They may start out the same, but after a while they become incoherent. The phase difference is not constant. What this has to do with atoms is that the electrons around the atom are entangled with each other. So here's a electron in a ground state and one in a higher state, and they're vibrating in place, and they're entangled with each other, hence the red and the blue. And because of that, that makes them coherent. And because they're coherent, you can write them as one big wave function. And this parlance that I'm talking about, you have one big wave packet that you can deal with. So because of coherence, you can have an entire atom become part of one thing. So the electrons around the atom are entangled and thus coherent, and even the nucleus can become part of this coherent thing even though it's not entangled with any electrons. So you have an atom and it's basically a big part of one big thing. And you hit it with a low energy photon and the whole atom will stay coherent and react to your collision. But if you hit it with a high energy photon, you can knock out an electron and ruin the coherence of the atom, and it's not a coherent mass anymore for a little bit. Now, you can even do this with molecules. So all the electrons around a molecule become entangled if you leave it alone and don't collide it with anything, and thus it's one coherent whole. And you can even get entire molecules exhibiting this sort of double slit behavior. And here you have 60 carbon atoms in a large sort of buckyball arrangement, and it's one big molecule. And if you leave it alone and let it become one coherent mass, you can basically see it reacting as one thing. Superconductivity and superfluidity are more interesting quantum phenomena. So when you get certain objects to low temperatures, the constituent electrons and atoms can be protected from other particles. All the thermal radiation stuff doesn't reach them, and they can relax and basically become one big wave packet, become a macroscopic quantum object. Now, the way this happens in a superconductor is the electrons can interact with each other and the positive charges around them and basically become what's known as a Cooper pair. Now, these are both spin 1/2 fermions, and fermions can't occupy the same state. But since they're basically now one big wave packet, then their spin becomes like a boson, an integer, and I think it's actually 0. So now that it's spin 0, it will basically behave like a boson overall. And so you have a whole lot of little bosons coming together and forming one big wave packet because they're all now allowed to be in the same state. And so now this big quantum object circulates around a superconductor with absolutely no resistance. And people have left the current in a superconductor going for years, and when they measure it, it hasn't changed at all. So this is a really useful phenomenon that we want to use even more than we do already. And superfluidity is another interesting one. It's kind of similar, but here you have atomic nuclei like helium nuclei, where the overall spin is an integer, and at really cold temperatures, it can basically start behaving like a boson as well. All the helium nuclei can basically exist in the same state. So they have interesting properties as well. First of all, the superfluid has no resistance, zero viscosity. So any little vortices that form will keep going forever. And also it also exhibits a strange creeping phenomenon where it'll creep out the sides of the container and so on. And it's, quite interesting. So now we can try to understand why we don't see quantum behavior of objects in our natural world, in our macroscopic world that we kind of inhabit. Well, let's sort of think through a few things. So for one thing, if an object does not collapse, we don't observe it in any way, shape, or form. So you can put your hands on a table and touch it and it's solid because all the quantum objects inside there are collapsing to a definite state. But there's lots of quantum objects called neutrinos going through you right now, and hardly any of them ever react with you. The vast majority go right through you and don't impart any energy or momentum into you, and they're basically going right through you as if you don't exist. Once in a while they might react with something. In fact, the vast majority of them go right through the Earth without interacting with the Earth. So if you had an object like a wall made out of neutrino-like particles, and even if it was as dense as lead, because you barely interact with these neutrino-like particles, you could walk right through the wall. Or if you had a table in front of you that was not collapsing, you would never even know it was there. You don't see it, you don't touch it, you just pass right through it. So this is one of the reasons how we can understand why objects behave classically to us. Like we can touch them, we can feel them, and they have definite states. And also, if something has collapsed into a definite state so that you can interact with it and touch it and see it and so on, then it's not in a superposition anymore. So you're never going to see something in a superposition. We can only infer that superposition happens from quantum theory, but we never actually observe it directly in superposition, because if you actually successfully observe it, it chooses a state. So we can't see something that's both alive and dead at the same time, or in many different positions at once. Once you actually successfully observe it, it collapses to a definite position and a definite state. And beyond that, objects at room temperature where we live are always collapsing constantly, because there's so much thermal radiation around. So many photons are hitting them that they're constantly collapsing and always achieving some sort of definite state. So this makes it so that objects around us cannot become all one thing, like a superfluid or something like that. So you're never going to see some strange behavior from a table or a fan in front of you, because it can't become part of one thing, and so it's not going to act like a big coherent wave packet. Also, even if you could make things become big objects like a baseball or a soccer ball become all one thing, even at room temperatures, the wavelength of such an object would be extremely small. So you couldn't throw a baseball through a tiny double slit or build up an interference pattern or something like that, because you can't build a slit size that small. And in any event, you can't make it coherent. So these are the basic reasons that you see the world in classically as we do, and we can understand it classically and deal with it classically. So we just don't see things in quantum superpositions or a part of one big wave pack or anything like that. The last thing I want to talk about is Schrodinger's famous cat thought experiment. Erwin Schrodinger was an early quantum pioneer who was doubtful that quantum mechanics was a complete theory, and he thought of this thought experiment to show that it wasn't. So what's the issue is that quantum mechanics is consistent with both collapse only happening upon measurement in a laboratory. And of course, humans are always involved in measurement in a laboratory. And this brings up the idea that perhaps without humans, quantum collapse just doesn't happen, which is a pretty absurd idea. But quantum mechanics is consistent with this view that until someone looks at something or observes something, everything is in superposition until that happens. But of course, quantum mechanics seems also to be consistent with collapse upon a proper interaction. So even when a human's not looking or doesn't exist, when two wave packets collide and interact properly, collapse can happen. So the whole idea that collapse only happens upon human measurement is pretty absurd, because for over 13 billion years before humans ever existed, that would mean that the whole universe was in some sort of huge superposition of states. And only when the first human was born like 1 million years ago and looked at those skies, suddenly the whole universe collapsed into one definite state, which doesn't seem very likely. So Schrodinger's cat experiment is sort of another way to see how this is fairly absurd. So suppose you place a cat in an isolated box so that no one can observe what's inside of it, no matter what they do, until you open the box, and you put a poison capsule in there for the purpose of killing the cat, and a hammer to smash the poison capsule, and a spin detector apparatus. So after you isolate the cat and close the box so no one can observe what's going on, a single electron is released from a source, and it goes through a magnetic field, and if it's spin up, it'll get detected. If it's spin down, the detector won't detect it. And then no poison will be released. But if it's spin up, the poison will be released because the hammer will fall and the cat will die. So if measurement is the source of collapse, and there's no measurement until a human looks, then until the box is open, the cat is in a superposition of both being alive and dead. And suddenly when it's opened, all that superposition instantly goes away, and you get either the cat being dead or alive. But this is pretty absurd, and that's was Schrodinger's point. So the thing is, though, if we assume that collapse happens upon proper interactions without humans existing or looking, then you don't really have to worry about this issue. And you can just say that whatever happened in the box when something interacted properly, then the cat either died or didn't die. And that's the end of the story. And I'd just like to acknowledge where I got the animations and images that I didn't make up myself.